Good afternoon. We'll wait for a few minutes for others to join. Hello, am I audible?
Yes, ma'am, you are audible.
Okay, is the presentation visible?
Yes, visible.
Okay. Okay, good afternoon. Welcome to the live session 7 for the course Basic Environmental Engineering and Pollution Abatement with myself Mahalakshmi S, Research Scholar from NIT-Trichy. So this is the general information. This live session for the course Basic Environmental Engineering, Pollution and Abatement will happen every Saturday from 3 p.m. to 5 p.m. I will be handling this live session. So the same Gmeet link, which is MDI, VDCP, NCG, can be used for all the Saturday sessions. And these live session videos will be recorded and uploaded on the YouTube channel. The name of the channel is Mahalakshmi S. You can find it through at Mahalakshmi Shekhar NATT ID. So we can note down this information for our next session also. So now, in this week 7, we will see the week 6 solutions, and then week 7 lecture overview, and also some sample question for your assignment 7, and some tutorial problems of your week 7 lectures. So now, coming to the first question of the assignment 6, which of the following is the correct order of treating the groundwater? Your week 6 is about the groundwater and surface water treatment, and also the treatment process like primary treatment, secondary treatment, all those things. So we'll be solving the questions given for your assignment 6. So the first question is, which of the following is the correct order of treating the groundwater? What is the correct order? So it involves 4 steps, which is aeration, oxidation, rapid mixing, and precipitation. So here we have to arrange this in a sequential order. So the right answer is aeration followed by oxidation. So in the aeration, you will be providing the oxygen. So with the help of O2, what happens? All the organic material will be oxidized. So the organic matter will get oxidized to form the simpler form of carbon dioxide and then water. So this is the most simplest product can be obtained through the oxidation process. So then with the help of the oxygen, we do the rapid mixing. So rapid mixing is allowing us to ensure that no sludge is formed without any reaction. So the continuous reaction is going to happen between the microorganism and the waste matter present in the water. And then what happens is the precipitation. Finally, after the complete reaction is finished, the precipitation of the sludge will happen. So the right order is aeration, followed by oxidation, followed by rapid mixing, and then precipitation. Now the second question is, which of the following process is used in the secondary treatment of wastewater? So the question asked is secondary treatment wastewater treatment involves which process they are asking. So in the primary treatment, so initially you are having a primary treatment, right? So here in the primary treatment, if you see, it is mostly to remove the solids. And then comes your secondary treatment. So coming to your secondary treatment, which is also called as the biological treatment, it is mainly to remove the BOD. So how this BOD is removed with the help of the biological organism. And then comes your tertiary treatment. So tertiary treatment is like mostly to disinfect your water. Here some of the BOD is removed and mostly it is like a purification process with the help of ozonation and then UV treatment. All these things you will be disinfecting the water. So here comes the disinfection. So the main aim of the secondary treatment is to reduce the BOD that is happening with the help of microorganisms. So among the options given, which process is used for the secondary treatment they are asking. Either it is ozonation or membrane separation or activated sludge treatment or both A and B. So now the right answer is activated sludge treatment. We know that ozonation uses the O3 to disinfect the water coming after the secondary treatment and then the membrane separation. This is also a kind of filter used for purification and activated sludge treatment is actually the method used for the secondary treatment. It involves using the microorganisms to degrade the organic components of the wastewater. So the right answer is activated sludge treatment. This is the process used in the secondary treatment of wastewater. So the next question is the treatment plant where effluents of a whole industrial cluster is treated centrally is known as. So we have seen in the previous class like the different effluents are there. So one is from household, which is called as domestic effluent, right? So in the case of domestic effluent, how these are removed? These are removed by using the STPs. So these are commonly treated in STPs, which is the sewage treatment plant. And then comes the industries, right? So this industries effluent is treated in two different methods, two different ways. So commonly, if the industry is one or two in the place, then it will be going to effluent treatment plant, which are called as ETPs. So in the case of whole industrial cluster, like this is the industrial zone, and there are many industries. Like say for example, more than 5 or 6 industries are there in an area. Then what happens? This area is called as the industrial cluster. These whole waste water effluent from these industries are commonly treated in the area called CETPs. The methodology will be same, but the name is different. And what happens after the treatment in CETP is these are further sent to the SPPs for the further treatment and to ensure the recyclability of the water. So whenever they are asking which treatment plant is used for the whole industrial cluster effluent, the answer is common effluent treatment plant. Now, the next question is which of the following treatment process or processes belongs to the tertiary treatment of wastewater? Just now I have explained like mostly this tertiary treatment is focusing on disinfection process. Why this disinfection is very important means since our secondary treatment is using a lot of microorganisms, right? So the microorganisms are very important to degrade the organic matter content in the wastewater. But on the other hand, we should ensure that these microorganisms are not passing to the discharging water. These waters after treatment are discharged into the river, which is again coming for our drinking water zone. So what is very important is disinfecting the water and ensuring no microorganisms on that. For that only the tertiary treatment uses different processes like ozonation, where O3 is used, and adsorption using some solid absorbing material, and then the reverse osmosis process. It is a kind of membrane type filtration. So the right answer is all of these. All the ozonation, adsorption, and reverse osmosis are the processes used in the tertiary treatment of wastewater. Next question is primary treatment typically removes the dash percentage of solids and dash percentage of BOD thereafter. So this primary treatment is mainly to remove the larger solid particles. So in the secondary treatment only we are using the microorganism and larger amount of BOD is reduced in the secondary treatment. So in the primary treatment only the most of the solid contents are removed. So the right answer is 60 percentage of solid content and 35 percentage of BOD content are removed in the primary treatment process. And some of the commonly used primary treatment methods are sedimentation. Okay, it works on the principle of gravity settling. So what happens based upon the size of the particle? These larger solid particles are removed in this primary treatment process. So the main principle is sedimentation and gravity settling. We have different chambers there to segregate these solids. And these solids again, we have seen like different solids are there. There is a total solid and these total solids are further classified into different types like total suspended solids and then total dissolved solids and total volatile solids. We have discussed this in the parameters of the water quality. Water quality. Now the next question is, what is the ratio of BOD to COD for efficient bioremoval process? Why this BOD and COD is very important means we already know the significant difference between the BOD and COD. BOD uses the biological material like the microorganisms to reduce the organic content. So this is called biological oxygen demand. And COD uses the chemicals like potassium dichromate to oxidize the organic content in the water, and those are degraded to simpler forms of carbon. So this is the major difference. When you see that since the COD using the chemicals, it can degrade both the organic as well as inorganic matter. So both the organic and inorganic carbon can be reduced by this COD. But in the case of BOD, since it is utilizing the microorganisms, so it can only degrade the organic matter. It cannot degrade the inorganic matter. So what happens is the COD will be always greater than the BOD. The value of COD is always greater than BOD. So this ratio of BOD to COD is very much important. Whether it can be a biorenewable process or not. Like if this ratio is significantly less means then these can be used for a biorenewable process. So obviously in the biorenewable process, we are going to use the microorganism for the treatment, right? Before going for this biological remediation, initially we have to know whether that wastewater can be treated with the biological process or not. For that, these parameters are helping us to decide to go for the biorenewable process or not. So now the right answer is BOD to COD ratio greater than or equal to zero point 0.5. So that what happens? We can decide whether it is efficient for the biorenewable process or not. So note down this ratio, and this is the significance of finding the BOD and COD in wastewater. Now, this question we have already discussed in the sample questions last week. The same question is repeated for your assignment 6 also. Match the type of settlings with their appropriate description. We know the gravity settling of what is going to occur. So in this one, we have seen a column like this. So it has different zone, right? So this is your P, which is hindered settling zone. And this is your Q, which is the discrete settling zone. And then there comes your R, which is the flocculent settling. And here it is the compaction zone, where the ultimately all the settling of particles would have completed. So in this zone, what is happening? So in the hindered settling speed will be uh, reduced, right? So right answer is hindered settling. It is a settling at a reduced speed due to the interaction with the neighboring particle. So here, first will comes Q followed by, here the order is different. So first comes the Q, next comes the P, next comes the. So in the Q, discrete settling, what happens? All the particles will fall with individual settling velocity. They are mostly same throughout the entire flow. So here, each particle falls through the equal depth in equal. So this is the first step of settling. And then comes the hindered settling. Here the settling speed will get reduced due to the interaction among the particles. Why? Because in this settling only, there will be a interaction with alum. Like any coagulating agent will be added so that the reaction with the coagulating agent will reduce the settling speed of the particle. So here again the settling will be more or less equal here. Here the settling will get decreased. And in the case of R, where which is third step. So in this step what happens? The flocculent settling will happen. Okay. Uh, this is the settling velocity of the particle increases due to the coalescence with the others. So here the interaction will come so that the reduced speed will get again increased. Now after the completion of the reaction, the flocks will be formed. So once the flocks are formed, these are larger in size, right? So these particles will settle down very fast. So again the settling speed increase. So in the compaction zone, since it is the extreme depth of this region, so the settling velocity will further increases. So this is what we have studied like. Here the y-axis is depth and the x-axis is t. So with respect to time, the depth of settling of the particles will get decreased. So initially particle will be here, then it will be here, then it will be here. After some time, all the particles will reach the bottommost region of the material. So this is how the settling of particles occurs. Initially, the discrete settling will happen where more or less the velocity will be equal, and then the hindered settling will happen where the velocity will get slightly reduced because of interaction. And in the flocculant settling, what happens? All the particles will settle very fast. So the settling rate will increase due to the formation of larger particle. And finally, in the compaction zone, the velocity is again getting increased rapidly because of larger size of the particles. The next question is aerobic digestion occurs in the dash of oxygen and anaerobic digestion occurs in the dash of oxygen. This is a very simple question, right? So aerobic means in the presence of O2 and anaerobic means in the absence of O2. So no O2 is there in this anaerobic and O2 is present. So the right answer is anaerobic digestion occurs in the presence of oxygen and anaerobic digestion occurs in the absence of oxygen. Now coming to the problem given in your assignment 6. So the question is a circular sedimentation tank fitted with a mechanical sludge removal unit is to treat 4 million liters of water per day. So 4 mld water are treated and then the detention time is 5 hours. So this is going to stay up to 5 hours in the tank. If the depth of the tank is restricted to 4 meter, calculate the diameter of the tank. They are asking you to calculate the diameter D of the tank. The capacity of the tank is calculated. So volume can be calculated using the given formula. Volume is equal to D square into 0.11 plus 0.785 H. Here H is the depth and D is the diameter. The right answer is 60 meter. We check the solution. So as the question has mentioned, 4 mld of water is used, right? So we know like 1 million is 10 power 6. So just multiply 4 into 10 power 6. And the detention time is 5 hours. Out of 24 hours in a day, only 5 hours is the detention time. So you have to again multiply it with 5 divided by 24 to arrive at the capacity of the tank. So 4 into 10 power 6 into 5 divided by 24 is 833 meter cube. So your value will be in liters. Since it is 4 mld, value will be in liters. We have to convert the liters to meter cube. So we know that 1 meter cube is equal to 10 power 3 liters. So whatever value you are getting, we have to divide it with 10 power 3 to arrive at 833 meter cube. So now we have found the capacity of the tank, which is the volume. And now using this equation, volume is equal to D square. We have to use this equation. Volume is equal to D square into 0.11 plus 0.785 H. Now the volume is known, which is 833, and H is also given. Here the depth of the tank is 4 meters. So H is 4 meter. We have to substitute 4 here, and then you have to solve this. If you solve this one, you will for 3 meter the answer is 18.38. We have seen this in the tutorial problem of last week. For 4 meter the answer is 16 meter. Okay, I hope you understand this problem. Do you have any doubt? Okay. Coming to the next problem, for a continuous flow settling tank, 3 meter deep and 60 meter long, what would be the flow velocity of water for effective removal of 0.025 millimeter particles? at 25 degrees Celsius. The specific gravity of the particles is 2.65 and viscosity of water may be taken as 0.01 centimeter square per second. So the data are given. The question asked is to find the flow velocity of the water. The answer is 1.125. We'll check the solution. So how you will arrive at the flow velocity of water? To arrive at the flow velocity of water, you have to use this relation. Okay, please note it down. So it is V divided by Vs is equal to L divided by H. So here to arrive at the flow velocity V, we have to find the settling velocity Vs. So this settling velocity is obtained by GdP square into rho P minus rho whole divided by 18 mu. So where G is constant, which is 981. 9.81, we are converting everything to centimeter, so 981. And rho P is 2.65, already given. Specific gravity of particle is 2.65. And for water, rho is 1. And then dP, diameter of the particle is given as 0.025 mm. So we are converting it to centimeter. So it is 0.0025 centimeter. We know 1 mm is equal to 0.1 centimeter. So I have to multiply it. And then now we have substituted all the known values like G is 981, rho P is 2.65, rho is 1, and dP is 0.0025 centimeter, and mu is given as 0.01 centimeter square per second. Substituting all the values, we arrive at the Vs settling velocity value as 0.0562 centimeter per second. Since the Vs is known and L and H are given in the question, we can easily derive the value of V, which is flow velocity. So here the L is given as 60 meter and the H is given as 3 meter depth. Now substitute the value 0.0562 into 60 divided by 3, which is nothing but V is equal to 1.125 centimeter per second. So this velocity is called as the flow velocity of the water. Okay. Do you have any doubt in the assignment 6 solution? Shall we move on to the week 7 content? Okay. I hope there is no doubt. So coming to the week 7, so this week is about the secondary treatment equipments. Mainly what are the process equipments used in the secondary treatment. So I have already explained what is the secondary treatment. Like in the primary treatment by gravity settling and sedimentation, the larger solid particles are removed from the wastewater. The organic matter content are decomposed into the carbon dioxide and water using the microorganisms in the secondary treatment. So in the secondary treatment, many equipments like activated sludge process and then trickling filter, lacunes are all used in this wastewater treatment, in the secondary treatment. So now this week 7 with the lecture 31 is about the activated sludge process. So we are going to discuss in detail about the activated sludge process. This is the schematic diagram of the processes involved in this activated sludge process. In this one, the major design parameters are F by M. So this F by M is the food to microorganism ratio. So what is the food here is? So the food is mentioned here as S. So this food is the substrate. So it is denoted as S in this cycle. So here the food is the organic content or organic matter present in the wastewater. So whatever organic material present in the wastewater is taken up by the microorganism as food for its growth. and this food is decomposed and it is going to form the sludge in this process. Okay. Next important parameter is the MLSS. So this MLSS is the mixed liquor suspended solid. So the solid particles are the food for the microorganism. Mixed liquor suspended solid MLSS is the aerated food. So after the influence of this wastewater into the aeration tank, we are going to agitate it vigorously. Like we are going to mix this material, influent wastewater, very rigorously so that it is going to form a mixed liquor suspended solid. Okay. Next parameter is MLBSS. So MLBSS is mixed liquor volatile suspended solid. So a portion of this MLSS is going to be taken up by the microorganism as a food. So that is termed as the MLVSS. Okay, that is going to be a volatile suspended solids. So all these things happen here in the aerated tank in this process. Once the influent is going in, the flow rate of the wastewater is given here as Q, and S naught is the initial amount of substrate. What is the concentration of substrate initially present in the wastewater? Okay, that is going to act as the food for the microorganism. So it is S naught. So here in this aeration tank, after mixing this waste material in the presence of air, it is going to form the mixed liquor, and a waste stream is once again taken from here, and it is going to the secondary settler, where after the complete reaction and decomposition, we are going to allow this wastewater to settle down here. What happens here is the clear water goes off as the effluent, and the sedimented sludge at the bottom is collected as the waste sludge here. Okay, two waste streams are here, and the effluent stream is here. And again, what we will do is to improve the process of conversion of organic matter to simpler carbon substances. We are again recycling this sludge. The sludge produced is again taken and it is given as the input feed here. So whatever organic material left undecomposed can again used as the substrate for the growth of the microorganism. So here the microorganism will continuously grow up in the aeration tank by taking the food present in the wastewater stream. Okay, and the clear water is collected from the secondary settling tank, and the sludge is collected at the bottom of this settling tank, and it is again recycled for the reaction. This is how this activated sludge process works. And the major assumptions here are you have to consider this process as completely mixed. This is one of the major assumptions. So that no microbial solids in the influent. So in the influent, there is no microbial solids. Okay. And then it is completely mixed here. It is a mixed liquor. And now the influent substrate concentration is constant. Whatever the influent is coming here is having a standard substrate concentration. It is going to be maintained constant. So this condition is to ensure the steady state condition. Okay. Now the solids based from the sludge recycle line also may be from the aeration tank. So whatever solids is removed here, it is from the aeration tank only. That is what we are going to assume. Next is the aeration. So for this process, from the explanation you would have known like the purging of air in this aeration tank is very important, right? This aeration can be done in different types. It can be a conventional aeration or tapered aeration or step aeration or complete mix. So you can refer this diagram if this is the tank length and this is the O2 demand there, O2 demand region and this is the O2 supply region. Okay. Initially, this demand is met by the O2 supply. You are just purging the O2 in that way. And now this is the so O2 supply is now the O2 demand is the same. Okay, this much O2 is required, and this is your O2 supply range. So we are aerating, and it is going to decrease after some time. and this is going to be constant for some time. And in the step aeration, we are just giving the O2 in stepwise manner. We are going to open the O2 circulation for some time and we are going to stop it for some time. So on and off conditions are included in this step aeration. And now in the tank, the fourth one completely means it is like we are going to purge the O2 entirely. The sufficient O2 is going to happen and the complete mixing of oxygen is going to happen. So these both are equal. Okay, this is completely met by the O2 supply. Now, with respect to activated sludge process, we have known the influent wastewater is going into the aeration tank, and by different aeration method, this mixed liquor is produced, and after reaction with the biological microorganism, it is going to the secondary settling tank where the sludge is formed and the clear water is collected. This waste sludge is also removed and it is also recycled for the second continuous process. So since we are assuming this process under the steady state condition, the mass balance of the microorganisms under the steady state condition is written as below. As mentioned here, the rate of inflow of microorganism into the system minus rate of outflow of microorganism from the system plus the net rate of cell growth in the aeration tank. It is not like the growth of microorganism is going to be uh, decreasing or it is going to be increasing. Both will happen. Okay, the microorganism will take up the food as a substrate and it will grow. After some period of time, it will again uh, die also. But there will be a certain growth rate maintained in this tank. So that is what mentioned here. If you see the inflow rate is given as Q into X naught. So X naught is the initial concentration of the microorganisms. And Q minus QW into XE plus QW into XR. So whatever is taken in the effluent stream and whatever is going to be withdrawn intermittently. That is the QW. This is the effluent stream. Okay. So this Q minus QW into XC and this QW into XR is taken as the rate of outflow of microorganisms from the system. Now the net growth rate is given as Rg into V for the particular volume. This is the rate of growth of microorganism which is mentioned as Rg. So Rg into P is equal to 0. We will use these parameters again to derive many other biokinetic parameters. Okay. Some other important parameters in this activated sludge process or the hydraulic retention time HRT and the mean cell retention time. How long the cells are retained in this aeration tank. That is the cell retention time. And the biokinetic parameter includes the Y. Y is the yield coefficient and Kd is the again as some rate constant for the decaying in the process and Ks is relevant to the substrate. So this is related to substrate which is the substrate concentration at the specific growth rate. Okay, and K is the maximum specific substrate utilization rate. It is the maximum utilization rate. Like only up to this level, the organic matter in the wastewater will be used for the growth of the microorganism. Okay, these are some parameters. Based on this, we have some problems to discuss. Okay, my voice is very low. Okay, I will talk louder. So now coming to the lecture 32, it is about the trickling filter, upflow anaerobic sludge blanket reactor and lagoon system. So these are the other equipments used in the secondary treatment process. So we will see this one by one. The first one is trickling filter. So in the case of trickling filter, as the name indicates, it is going to use a filter medium to treat the wastewater. So this is the diagram of working of a trickling filter. You can see it is going to be like this. It is a tank like this, and in between you can see this medium, right? So this is the filtration media where you will be having the microorganisms, okay? And then this is the influent passing area, and here you are also purging the air for the growth of the microorganisms. So the water is going to flow here, and this is the domed enclosure, and this is rotating influent distributor. Again, the influent is distributed here as sparkles also from the top, and the influent is again they are supplied at the bottom also. Okay, the main concept is, as they said, the waste materials will be like this. Okay, very complex waste material will be like this, and the microorganisms will utilize this waste material. Say, for example, one or two cells are there, microbial cells are there. So these will use these waste material, and these microorganisms will grow in size. So these cells will become larger, and again these cells will also multiply into n number of cells. All these will happen only by the uptake of the waste matter as the food for the microorganisms. Okay, so the way in the trickling filter, the wastewater trickles down through the filter media. This is the filter media. So the wastewater is going to fall down over this media. When it is passing through it, there will be a formation of sludge like this. Again and again, after consumption of some portion of organic matter, the microorganism will grow in slice, and this biological material will fall off after some period of time. That process is called sliming. So that is the falling off of the organic material utilized by the microorganism. Okay. So now the filtered water will be again collected in this clarified tank. So whatever the sludge produced, that after sliming there will be a falling off of the sludge. So those are collected from this clarifying tank, and the clarified water present on the top will be collected as the treated water, and then it can be again treated by recycling it, or it can be also passed to the distribution system. So typically this medium will has rock, sand and synthetic plastic. This is the composition of the filter media, and the microbial film, which is the biological slime. So this is coated on the media. When the microorganisms grow up in size and grow in numbers, this slime will become very thicker and it will fall off after some time. So with the clear water, the slime is also collected, and this is collected as the sludge. Okay. Now, these are again classified into low rate filters, high rate filters, super rate filters. So the composition is the major difference in these filters. So in this one, low amount of organic load will be there. Okay, and here high amount of organic load will be there. In the super rate filters, what typically this filter material is composed of is the plastic. So this is classified as the super rate filters. Okay, plastic materials are used here for the filtration medium. Now coming to the next method, which is upflow anaerobic sludge blanket reactor. We know that anaerobic is a condition where no O2 is utilized for the treatment of wastewater. So whenever the O2 oxygen is involved, the product will be carbon dioxide and water. Whenever no oxygen is involved, then ultimately your product will be what? Methane gas. So this is very important. So that whenever the anaerobic process is taking gas, your product is methane, right? So this is the diagram of your upflow anaerobic sludge blanket reactor UASB. So here if you see the inclusion material after the grit removal, like the solid particles are removed, it is passed in here, okay, and here it forms a sludge blanket. So here no oxygen is there. So this sludge will be anaerobically decomposed to produce the gas called methane. All these gases are collected in the overhead of the tank. So this is the overhead region of the tank where the gases will be collected. Okay, and wherever the sludge is not entirely solid, it will be a solid liquid sludge, and now it is also producing a gas, right? So now it is producing a gas, so this gas liquid is separated, and the pure biogas is collected from the top. Finally, the treated water is again collected from the tank. So this is how the anaerobic sludge blanket reactor will work. So in this thing, the sludge age days, how long we are going to close this tank and maintain the sludge for decomposition means that is the sludge age. It is given by the values, the ratio of total mass of MLSS in aeration basin divided by daily mass of total suspended solids in the influent. So this ratio gives you the sludge aging days. Okay, and then the mean cell residence time age is given by total mass of MLSS in the aeration basin divided by mass of SS wasted per day plus mass of SS in effluent per day. So these are the two formulas used for calculating the sludge age and the mean cell residence time age. So now coming to the lagoon system, so it is mostly a pond system. We have discussed in detail in the previous class. Like this can have aerobic medium as well as the anaerobic medium. So the aerobic medium is mostly the external O2, atmospheric oxygen. So the atmospheric oxygen is incorporated into this lagoon system, and here the aerobic decomposition occurs. So CO2 and H2O will be formed here. Okay, atmospheric oxygen is also fixed, and the microorganism will utilize the uh, waste material, and it will produce carbon dioxide and water. Now, in the anaerobic region, so this is the sludge region at the bottom where there is no oxygen present. So here what happens, again the methane gas will be formed. So both aerobic and anaerobic conditions are prevailing in the lagoon system, and this air can be atmospheric oxygen, or it can be from any external aerators, like mechanically or providing the aeration. Okay. Now the flow rate is mentioned as Q, and S naught is the initial substrate concentration, and here the Q is again the flow rate, and S is the outlet concentration of the wastewater stream by using the mass balance. So in this one also, we are defining the efficiency in the terms of BOD removal. Okay, so mass balance is based upon the BOD. So the BOD in is equal to BOD out plus BOD consumed. So in is flow rate into substrate concentration, it is QS now. Out is Q into S, and BOD consumed is B into KS. Okay, so in this equation, I am taking QS as common. So if we take QS as common, it will become 1 plus 1 plus V by Q into K, right? So it will become like this. Now QS naught is equal to QS naught is equal to QS into 1 plus V by Q K. Okay, so Q and Q will get cancelled. To arrive at this, this will come this side and this will go to this side. So now what happens? S divided by S naught is equal to 1 divided by 1 plus K into V by Q. We know that volume divided by flow rate is theta. Theta is equal to V by Q, right? So S by S naught is equal to 1 divided by 1 plus K naught, oh sorry, K theta. So this is the equation which can be used for solving the upcoming problems. Okay. So now we have seen the secondary treatment equipment like activated sludge process. Next is the tripling filter, and then is the upflow anaerobic sludge blanket reactor, and finally the lagoon system. Okay. So now we will see some other methods. So in the lecture 33, it deals about the sequential batch reactor and granular activated sludge process and membrane bioreactors. So coming to the sequential batch reactor. So what is the major difference means? It is also mostly like ASP, but in ASP what happens is you see this diagram, the inflow of wastewater is happening here and aeration is happening here, and there is a separate secondary settling tank from which the sludge and the clarified wastewater is removed, right? There will be different sections in the different treatment steps. But here, in the sequential batch reactor, here it is happening in different places, right? But this sequential batch reactor will happen only in a single tank. So all the mixing, aeration, settling, uh, removal of the supernatant, everything will happen in a single tank. So that is the major difference between ASP and the sequential batch reactor. So only a single tank is used in the sequential batch reactor. There is another method called continuous ASP. So the continuous ASP can use different aerating tank. Okay, and but it is not similar to the sequential batch reactor because it uses only one tank in which all the reaction is going to happen. The steps involved in the sequential batch reactor is filling, reacting, settling, decanting, and idle stage. Okay, so this filling that's the first step. So the influent wastewater is coming in. So we are filling the wastewater in the reactor, batch reactor. So where the mixing and aeration is going to happen. We are going to mix the wastewater and we are also providing the air here. Now the reaction will happen. During the reaction also, the filling is stopped. No incoming wastewater is there in the react stage. So the incoming wastewater is cut off here, but the mixing and aeration continues. We are going to mix the water and again we are going to aerate the water so that the reaction will happen in the reactor. Now the next stage is settle. So in the settle stage, after the completion of the reaction, what we are going to do is we are going to cut off the mixing and aeration. So no mixing, no aeration happens. There is only settling. Okay. Now in the decant stage also, you are not going to do any mixing or aeration. So you just cut off the mixing and aeration. Now after settling, the clarified water is here on the top, right? And the sludge is here at the bottom. So first the treated wastewater is removed in this decant step. And now coming to the idle step, where this waste sludge is again removed from the uh, reactor. Okay. Again, what happens? The influent wastewater is filled in this tank. We are providing the aeration and mixing. Now the reaction is going to happen, and again settling happens. Decant the supernatant, which is the clear treated wastewater, and the sludge is going to remain there. Finally, collected. So this cycle continues. So in this one, we have a different kind of filling, which includes a static filling, mixed filling, and aerated filling. Okay. So the static filling is this filling of the waste material into it. Mixed filling is involving mixing. So mixing means mechanical mixing will happen. We use equipments to mix the wastewater. Okay. So now in the aerated region, what we will do is we will use the aerator. We will supply O2 as well as there will be a mechanical mixing. So these are the different type of filling in the batch reactor. Okay. Now, the efficiency of the wastewater treatment in the sequential batch reactor depends upon many parameters, which includes the cycle time. So, how long the detention time is there, how long the reaction is going to happen, how long you are going to allow it to settle down. So, all these cycle time, one cycle time is very important. Usually, it is 4 hours. Okay? And then the volume exchange rate. So, how much volume is going to be filled and refilled again and again? How much is going to be taken out, how much is going to be filled, what is the volume exchange rate. Next is the hydraulic retention time. Again, what is the retention time for each and every wastewater. Next is the solid retention time. How much time the water is retained, how much time the solid sludge is retained. Both are very important to ensure the efficiency of treatment process. Next is the nitrification and denitrification. So these are the steps involved in uh, the sludge decomposition. Okay, so how much nitrification and denitrification is going to happen. That determines the efficiency of the process. Okay. This is all about the sequential batch reactor. Now coming to the granular activated sludge process. Again, this is also an activated sludge process. The only difference is we are going to use the granule. So it uses the granules of microbes instead of floc. So how this granules will be means, so this is the typical example of this GASP. This is the whole granule. All the process occur using the single granule. So in the single granule only all the process are going to happen. And this granular activated sludge process is using the technology called Nerada technology. This is found in the university in Netherlands. Okay, which is named as Nerada technology. What is going to happen here is in the single granule itself, we are having the different zones. The innermost zone is called as anaerobic core, and the middle zone is called as anoxic layer, and the outermost layer is called as the aerobic layer. So what is happening here in the outer layer is the biological oxidation of organic matter is happening and nitrification also happens. So where the CO2 plus O2 gives CO2 plus H2. The product is CO2 and H2. And also the nitrification. So the ammonia in the presence of oxygen is converted into NOx. Okay. So nitrification is going to happen. Oxidation of nitrogen is happening. And in the anox layer, denitrification is going to happen. So the NOx NO2 is going to become N2. Only nitrogen is going to be released. So denitrification is going to happen. And the biological phosphorus removal. So the phosphorus orthophosphate, it is going to be polyphosphate is going to be converted into orthophosphate here. Okay. And the orthophosphate can also multiple forms form the polyphosphate alkane. Okay. These are the reactions going to happen in the anoxic layer. So this is a single granule where the aerobic reaction happens and anaerobic reaction also happens. So this granule consists of the microorganism. So whatever the wastewater come in contact with the granule, what happens is the microbe will take up the nutrients from the wastewater and they will undergo all these reactions to treat the wastewater. So this is the graph showing the oxygen content in each region. So in the outermost region, it is very high. When it is reaching the middle region, it is decreasing rapidly. And in the innermost layer, it is zero. Okay, this is straight line. Okay, this is all about the granular activated sludge process. Coming to the next equipment, membrane bioreactor. So this is a reactor consisting of membrane. So this membrane is nothing but microorganism enclosed membrane. So it is a suspended growth biological reactor. We already know what is the suspended growth and attached growth. So attached growth is microorganism is going to be othered to one medium, that is attached to a particular medium. So in the case of suspended growth, microorganism is freely floating. It is suspended in a particular medium. So it is a suspended growth biological reactor combined with the membrane unit. So now this is the diagram of membrane bioreactor. So here the wastewater is coming in. It is agitated using mechanical instrument and it is next aerated. So now with respect to aeration, the microbial organism will grow in numbers, take up the organic material. And now in this region, this is the membrane filtration. So aeration membrane system is here. So where the biological organisms are just taking up the waste material and the treated water is also clarified here itself in the membrane system. So the treated water is taken out for reusing purpose and the sludge form is collected and it is removed here at the bottom. So this is the working of membrane bioreactor system. So now we have seen different methods in the secondary treatment and some other methods given in the lecture 34 are the phytoremediation and phycoremediation. So as the name indicates, remediation. So both are remediation system. It is going to remove the unwanted substances or any remove the contaminants or pollutants from the some region. Okay, from the some region. Here it is the water, right? From the water is going to remove the contaminants by using some other external sources. So in the case of phytoremediation, so phyto means green plants. How these plants are used to remove the contaminants present in the water means that is very interesting, right? So some plants have the detoxification properties. We are using such kind of plant like there are specific plant for chromium removal, specific plant for lead removal, specific plants for zinc removal. So these are all used for the detoxification purposes. Okay. So if you see this diagram, this is a general diagram. So the tree roots taking the water and the pollution from the ground. So this is the water table. So polluted water is here. So you can see the polluted water here. So this is the polluted soil. So the tree is taking up the water. Okay, the water enters the tree where the pollution is cleaned up. So here in the body of this tree, the pollution is cleaned up, and again this region will become a cleaned soil, and the clean groundwater will be present here. Okay, so how this is happening means it is mentioned here. Movement and detoxification of heavy metals in the plant cell. In the plant cell only, all these heavy metals, for example, copper, cadmium, lead, and zinc, all these are used as phytochelators. So these will take up the metals, these metal chelators. These will be used for the growth of the plant and the detoxification sequestration happens in the cytoplasm. So these heavy metals are used for the growth of the plants. It is fixed in the plant cell itself, so that these heavy metals are removed from the groundwater system they are taking. Okay, this is how the plants are used for remediation of water. And the next thing is phycoremediation. So the phycoremediation is the advanced process. It is going to use algae. So whenever we are speaking of algae is generally of two types, which is macroalgae and the other one is the microalgae, right? Macroalgae are larger in size, so this includes the seaweed. Okay, microalgae are smaller in size. We can only view them with the help of microscope. The most commonly used microalgae are spirulina species, chlorella species. So these are some of the examples of microalgae. Okay, so here the algae is used for the removal of contaminants, and algae requires sunlight for the growth. Uh, Generally, these algae are cultivated in two different methods. One is open system, another one is closed system. Okay, as the name indicates, the open system is more open to the aeration and it is directly kept under the sunlight and all. So this open system includes the examples of raceway ponds, open pond system, raceway ponds, tubular ponds. So that different shapes of ponds will be there like this. In an open pond, you will be cultivating the algae. But in the case of closed system, in smaller scale, it will be cultivated in the lab, okay, under the artificial light condition. But in the larger scale, it will be cultivated in photobioreactors. So these are the equipment used for cultivating the algae. So it includes different types like horizontal photobioreactor, vertical photobioreactor, flat panel photobioreactor. So in this way, the algae is cultivated. Cultivation is nothing but growing of algae. So these are some of the examples. So these are the horizontal tubes. You can see the horizontal tubes are used. So in this tubes, the algae is cultivated. Okay, and this is the vertical tubular system. So this is a vertical tubular system, and we are passing air bubbles. Okay, so this is called as bubble column vertical tubular system, and this is the air lift. So we are having a channel in which the algae is cultivated, and we are passing the air in the medium in this way. So like this, the air is continuously circulated here. So this is again another type, air lift type. And next, this is the flat panel. So these are the panels. So in the panels, the algae is cultivated. And another method is the plastic bag. So this plastic bag is nothing but cultivating of algae in the plastic bags. Okay. Uh, why algae is a prominent method to remove the pollution or the contaminant in the water means it is very easy to grow, and there is no requirement of absolute clean water for the growth of algae. So algae doesn't require a very clean water to grow. So in the wastewater, algae can grow. Even in the black water with some external nutrients, we can grow the algae. So all the brackish water can be treated by using the algae. And lesser area is required for the cultivation of algae. And if you see, many value-added products from this algae can be obtained. And for example, we have spirulina tablets like right. It is rich in fatty acid. It has purfa-rich material, and the pigments can be obtained from algae. Also, carotenoids are very value-added products obtained from algae, and we also know that this algae can be used for fuel generation, right? So from the algae, we can produce biohydrogen, we can produce biodiesel, and we can also produce bioethanol also from algae. So this algae is a potential source for multiple products. And one of the major advantage is this algae uh, does not require the pure water for its growth. So the wastewater can be treated using the algae. So water is also getting treated. We also obtain the value added products from the algae. That is the major advantage. Next is the harvesting of algal biomass. After harvesting only, I am telling all these products can be extracted from the algal biomass. So how this algae biomass is extracted means, so this is a combination of our wastewater and algae, right? So once the clear water is to be separated from the algae, we can go for filtration, centrifugation, these methods, and we can separate the algal biomass from the water. The water can be used for other purposes, and the algae can be used for value-added product extraction. Okay. So this is all about the week 7 lecture overview. Now we will discuss the sample questions of assignment 7. Okay. Coming to the week assignment 7 sample question. The first question is, which of the following statement is true about the high rate activated sludge process? So what is the right answer? So in a high rate activated sludge process, what is true they are asking? Required short aeration period and sludge production is high. Required high aeration period, sludge production is low. Required high aeration period and sludge production is moderate. None of the above. What is the right answer? The high rate activated sludge. Okay. The answer is short aeration period, sludge production is high. So this is always contradictory only. Why? Because if you are providing less amount of O2, what happens? The organic matter will not be efficiently converted into CO2 and water. This reaction mechanism will be hindered in the uh, absence of the adequate amount of oxygen. So when there is a shorter aeration period, most of the organic matter will be collected in the sludge, will be collected as sludge. So the sludge formation will be higher in the presence of lesser amount of oxygen. The right answer is required short aeration period and sludge production is high. The second question is for a good sledge. So, if the sledge is said to be a good sledge, the value of the sledge volume index should be in the range of. So, this is the value. So, this SPI, which is the sledge volume index, should be 40 to 100 only. Then only it is called as a good sledge. Like most of the organic matter is utilized, only the residue is uh, collected as the sludge. Okay, that is what a good sludge is indicating. And the value of 40 to 100 SPI is mentioning the sludge is good. Now, which of the following material is more preferable as a packing media in super rate trickling filter? We know high rate trickling filter, low rate trickling filter, and super rate trickling filters are there. Based upon the packing media, these filters are classified into three types. So, which material is used in the super rate trickling filter? What is the right answer? Is it stones, corals, synthetic plastic, or sand? We have discussed it, right? So the synthetic plastics are the materials mainly used in the super rate trickling filter. The right answer is synthetic plastic. The term sequential batch reactor comes from sequence of steps the reactor goes through as it collects the wastewater, treats it, and then discharges it. All these steps are performed in 4 tanks, 3 tanks, 2 tanks, single tanks. We have seen this sequential batch reactor, right? What is the right answer? It is happening in a single tank. So in a single tank only you are filling the material. After filling the material, what happens? After filling, mixing happens, right? After mixing, you are allowing it to settle down. And then you are going to decant. Decant what? Decant the treated water. Then you are going to keep it as idle to remove the sludge. Again, you are going to fill the wastewater and the process continues. So this is the process involved in the sequential batch reactor. So all the processes are going to happen in a single tank. During the operations of a sequential batch reactor, the idle step occurs between decant and dash phase of next cycle. Between the which two steps this idle step is coming thereafter. React, settle, fill, none of the above. So this is the idle stage that is going to happen between decant and filling, right? So it is going to occur between decant and fill phase of the next cycle. So now the next question is solid retention time SRT determines the time for which the biomass is retained in the reactor. So SRT for the SBR system may be given as. So how this SRT can be mentioned? What is the correct equation they are asking? Where X is the MLSs, mixed liquor suspended solids in the reactor with fulfilled in mg per liter, and XW is the MLSs in the waste stream, and VW is the waste sludge volume, and VT is the total working volume of the reactor, and TC is the total cycle time. So what is the right relation they are asking? So the correct answer is SRT is equal to, so solid retention time SRT is equal to, first we have to write the general VT, which is the total working volume of the reactor, into X. So X is the MLSS with fulfilled, okay, the reactor with fulfilled. So initial X, it is mentioned as uh, X here. This MLSS is the X here. And now TC is the total cycle time. So VT into X into TC divided by 24 into VW. So now VW is the volume of water you are collecting as waste sludge. Okay. Now XW is the MLS, it's like a microorganism, mixed microorganism in your waste stream is mentioned as step. Okay, this is the solid retention time equation. Which of the following is a type of open photobioreactor? So they are asking about open photobioreactor. So the answer is raceway pond, this pond. Okay. Now identify the type of photobioreactor present in the below picture. So what is this type of reactor? Vertical column photobioreactor, horizontal tubular bioreactor, plastic bag system bioreactor, raceway pond bioreactor. So this is very simple, right? So the algae is cultured vertically. So this is vertical column photobioreactor. So now we will solve some problems in this week 7 lecture. The question given here is a complete mixture activated sludge process is used to treat the wastewater flow of 2 ml. So the flow rate is given as 2 million liters per day, having the BOD 5 of 250 mg per liter. The biomass concentration in the aeration tank is 2500 mg per liter. So the biomass concentration is nothing but your X value. Okay, and the concentration of net biomass leaving the system per day. So this is the biomass concentration in the aeration tank, and the concentration leaving the system is 70 mg per liter. And the aeration tank volume is given as 250 meter cube. What is the hydraulic retention time of water in the aeration tank? So the retention time is asked for the wastewater in the aeration tank. So we can see solution now. So the first question asked is hydraulic retention time, HRT. It's nothing but V by Q, right? So the volume is given as 250 meter cube. That is the volume capacity, which is the volume of the aeration. And Q is the flow rate. So the flow rate is mentioned as 2 ml. So it is 2 into 10 power 6 liter, which is nothing but 2 million liter, right? So this is 2 ml D. So we know 1 meter cube is 1000 liter. So liter to meter cube, we have to multiply it with 10 power minus 3 meter cube. Okay, now we have converted this liter to meter cube. Liter will get cancelled. Meter cube will get cancelled. So now we have 125. 250 divided by 2 is 125. 10 power 6 and 10 power minus 3 are there. So 10 power 3 in your denominator. So which is nothing but 0.125. Only days are remaining. Right? So days. This is the answer. So the question asked is, what is the hydraulic retention time of wastewater in the aeration tank? So this HRT is given by the equation V divided by Q. V is the volume of the tank, which is 250 meter cube. Q is the flow rate of the wastewater. Here it is given as 2 MLD, 2 million liters per day. We are converting the liters to meter cube by multiplying it with 10 power minus 3, and you are obtaining the value of HRT as 0.125 days. Okay. Next question is to calculate the mean cell residence time. Okay, a different question. A completely mixed A completely mixed activated sludge process is used to treat the wastewater flow of 550 meter cube per hour, having soluble BOD5 of 200 mg per liter. So the wastewater flow is given as 550 meter cube per hour, and the BOD range is given as 200 mg per liter. The concentration of the soluble BOD5 escaping the treatment is, so escaping the treatment is 20 mg per liter. So the wastewater leaving the treatment having 20 mg per liter of BOD. The same criteria are as follows: y is equal to 0.5, k is equal to 5 per day, KD is equal to 0.05 per day, Ks is 80 mg per liter, and the concentration of MLBSS, excess given as biomass concentration, is 2000 mg per liter. Compute the mean cell residence time theta c. This is the question. So this is very simple. So this is the activated sludge tank. So the flow rate Q is mentioned here as 550 meter cube, right? 550 meter cube per hour, and your X is given as 2000 mg per liter. That is the initial concentration of your biomass. Now the BOD in. So your BOD in is 200 mg per liter, and while leaving it is having only 20 mg per liter. Rest are all consumed. And other design parameter like y is equal to 0.5, k is equal to 5, kd 0.05, k is 80 are all given. Now to compute the value of theta c, the formula is 1 by theta c. This is obtained by considering the steady state condition, and by mass balance this equation is derived. Okay, 1 by theta c is equal to y into y into k. Okay, here k is mentioned as 5d, right? K into Se divided by Ks plus Se. Here S not given. Okay, minus Kd. This is the general equation to obtain the theta c, which is the mean cell residence time. Okay. Now y is given as 0.5, k is given as 5, Se, it is the effluent substrate concentration. When in the effluent stream, 20 mg per liter is there. So we have to substitute 20 here. So 0.5 into 5 into 20 divided by Ks is given as 80 mg per liter and SE is again 20 mg per liter. Okay. Kd is given as 0.05. If you substitute this value, you'll obtain 0.45, which is 1 by beta C. Take the reciprocal of it. So the answer is 2.22 days. This is the right answer. So this is the beta C mean cell residence time. Do you have any doubt? Any doubt so far in the sample questions for assignment 7? Okay, if no doubts are there, we will continue to tutorial questions. We will solve the problems for the week 7. Okay. So coming to the first question in tutorial 7, the question is a complete mixture activated sludge process is used to treat a wastewater flow of 2 mLD having the BOD 5 of 220 mg per liter. The biomass concentration in the aeration tank is 2300 mg per liter and the concentration of net biomass leaving the system per day is 50 mg per liter. Aeration tank has a volume of 200 meter cube. First part is to find what is the hydraulic retention time HRT of the wastewater in the aeration tank, and the second part is to find what is the mean cell residence time. So these two only we have found in the previous problem. So in this question we have found how to find the HRT, and in this question we have found how to find the mean cell residence time. So this question is the combination of these two. So this is the activated sludge process. Okay. So in this process a complete mixing is going to happen, and the inlet flow stream, outlet flow stream are this one, and the flow rate of the wastewater is 2 mLD. So now the flow rate is 2 mLD, which is nothing but the Q. Okay. Q is equal to 2 mLD. And the BOD 5 of 220 mg per liter is having for the influent water. So it is nothing but your substrate concentration. Initially, your S naught. Okay. S naught is nothing but 220 mg per liter. And then the biomass concentration in the aeration tank, which is your X. Okay. Is 2300 mg per liter. And then the concentration of the net biomass leaving the system per day is 50 mg per liter. So as effluent, in the effluent stream, SA is equal to 50 mg per liter. So in the inlet stream, there are 220 mg per liter, and in the outlet stream, in the effluent stream, there are 50 mg per liter. So this BOD corresponds to the substrate concentration. And the aeration tank volume. So the volume of the tank is given as 200 meter cube. Okay. So these are the given data. Q is equal to 2 mld. We have to convert this. So this is 2 into 10 power 6. Million is mentioned as 10 power 6 liters per day. Right. And again BOD 5 is 220 mg per liter. MLSS is 2300 mg per liter. XW is 50 mg per liter. And then V is 200 meter cube. So now HRT. The first question is to find the hydraulic retention time. So your HRT is given by the formula V by Q. Volume is 200 meter cube divided by Q is 2 into 10 power 6 liter per day. We have to multiply it with 10 power minus 3 to convert it to convert the liter to meter cube. Now you will obtain the HRT as 0.1 days. Okay. And theta C is the mean cell resonance time. It is given by total biomass present in the system divided by net biomass leaving the system per day. So the total biomass in the system is given as 2300 mg per day. Okay, this is for per liter, and you know the volume of the tank is 200 meter cube. To find the total biomass present, you just multiply the 200 meter cube into 2300 mg per liter. Now convert the meter cube to liter, so into 10 power minus 3. So 200 into 10 power 3 into 2300. So again this mg is converted to kg. Finally, you will obtain the value of 460 kg. This is the total amount of biomass present. Okay. Now the net biomass leaving the system is the flow rate is again 2 ml, and here the leaving concentration is 50 mg per liter. Okay. This is not the substrate concentration. Sorry, this is not the substrate concentration because it is not mentioned as the BOD leaving, it is given as a biomass leaving. Okay, so it is the biomass leaving. So this is the XW. This is the biomass leaving. So what is the amount of biomass totally leaving per day means? So if you have to again multiply it with the flow rate. 2 into 10 power 6 liter per day into 50 mg per liter. So liter will get cancelled. So it is 100 into 10 power 6 mg per day, just nothing but 100 kg per day. Now we know the total amount of biomass initially present here and total amount of biomass leaving here. Everything is calculated for per day. Okay. So now the theta C is equal to total biomass present divided by net biomass leaving, which is 460 divided by 100 is equal to 4.6 days. So this is the theta C value. Okay. So in this question, we have obtained the theta C using this formula because the values of y, k, kd, ks, everything is given. So we have to go for this one. And the BOD escaping is given, BOD incoming is also given. So all these are given. So we use this formula. Now we don't have the details of the biokinetic parameters. Instead, we have the value of direct biomass concentration in the incoming wastewater and the biomass concentration in the outgoing wastewater. So we are calculating it directly, very simply by multiplying it with the flow rate and multiplying the MLSS into the volume of tank. Okay, this is very simple question. Now the next question is a completely mixed activated sludge process is to be used to treat the wastewater flow of 510 meter cube per hour, having the soluble BOD5 of 240 mg per liter. The concentration of soluble BOD5 escaping the treatment is 11 mg per liter. So now the incoming BOD, outgoing BOD are given. So these are all related to what? These are all related to the substrate concentration. Since it is given as BOD5, is corresponding to the substrate concentration. So the S naught is 240 mg per liter and SE is 11 mg per liter. Okay. Now the biokinetic parameters are given, which is y is equal to 0.4, k is equal to 4, kd is equal to 0.07, ks is equal to 90 mg per liter. And the concentration of MLBSS is also given. So X is the biomass concentration, which is nothing but 2000 mg per liter. With these given data, they are asking us to compute the following parameters, which is the treatment efficiency, mean cell residence time theta c, hydraulic retention time theta, volume of the aeration tank, and F by M ratio. Okay. So the efficiency of the activated sludge process depends upon the reduction of BOD level. Okay, how much BOD is reduced is the treatment efficiency. So eta is equal to S naught minus SE divided by S naught. Incoming BOD is 240 and the outgoing BOD is 11. So outgoing wastewater stream is having 11 mg per liter. So you have to divide it again with 240. So the percentage is 95.42 percentage. That's the efficiency of this activated sludge process. Now to calculate the theta c, we have all the biokinetic parameters. So 1 by theta c is equal to y into k into sa divided by ks plus se minus kd. Okay. So this is the formula we have previously used also. So y is zero point 0.4, k is 4, SE is effluent of BOD is 11 and KS is 90 plus SE is again 11. So if, KD is 0.07. Everything is given in the question itself. So if you solve this one, you'll obtain the theta C value of 0.104 and you have to take the reciprocal of it to obtain the value of theta c. So 1 by theta c is 0.104. So theta c is 9.61 Ks. Okay. The next question is to calculate the hydraulic retention time. Now we don't know the volume of the tank and the flow rate is given as 510 meter cube per hour, but volume of the tank is not yet known, right? So the hydraulic retention coefficient should be determined, retention time should be determined in a different way. Like we have to use this formula. So these are all the formulas obtained from the mass balance of the activated sludge process, where theta is equal to theta c into y into s naught minus se divided by x into 1 plus theta c into kd. So theta c, just now we have found it as 9.6 and y is given as 0.4 and S naught minus Se is 240 minus 11 mg per liter. X is the biomass concentration, which is nothing but 2000 mg per liter. And 1 plus theta c is again 9.61 and Kd is given as 0.07. If you solve this one, you'll obtain the theta value of 0.263. Now you need to find the volume of the tank. So we have found the treatment efficiency with the help of initial and final POD and the mean cell residence time is obtained by using the biokinetic parameter and the hydraulic retention time is also obtained by using the biokinetic parameters. And now the volume of the tank is obtained by the simple equation. We know that theta HRT, hydraulic retention time is equal to P by Q. Now we know the flow rate, which is 510 meter cube per hour, and theta is 0.263 per day. Since it is flow rate is in hours, just multiply this 0.263 into 24. Okay, per day has 4 hours. So if you multiply this one, you'll obtain theta in terms of hours, which is 6.31 hours. And the volume of the aeration tank is given by V is equal to Q into theta. Q is 510 meter cube per hour into 6.31 hours 3218.1 meter cube. So the next part of the problem is to obtain the F by M ratio. So we know that F by M ratio is the food to microorganism ratio. It is given by the relation Q into S naught by Vx and this Q by V. Okay, V by Q is equal to theta. So Q by V is 1 by theta. Okay, F is the food. So the food is the QS naught. Okay, this is QSV. The food is the QS naught. And the microorganism is the this is the volume of the tank and this is the X biomass concentration in the tank. So M is given by Vx, Q is not by V into X. So this Q by V is substituted with theta S naught divided by theta into X. Right. So now we know the value of theta 0.263 and S naught is 240 mg per liter is given in the question and X value is 2000 mg per liter. Let's substitute all the known values. We will obtain 0.46 mg per mg day. Okay, this is the food to microorganism ratio. This is how we are solving the activated sludge process based problems. Now, another problem based on the activation sludge process is given here. So here the question is the air supplied to the activation sludge plant of the previous example. So we have to take the previous example. Uh, so here you have to assume that air is supplied at a temperature of 25 degrees Celsius and the oxygen transfer efficiency. So efficiency of oxygen transfer is only 10%. Assuming the BOD 5 is 67.5% of the ultimate BOD. So the ultimate BOD refers to the maximum conversion of organic materials. So the BOD 5, 5-day BOD is 67.5% of the ultimate BOD. That is what given in the question. Now we are supposed to calculate the volume of air supplied to the plant. So you have to find the volume of air. So volume of air is obtained by determining the amount of air supplied. So for that we need to find MO2 before finding the volume of air. Okay, MO2 is the amount of air, that is the mass of oxygen required per day, which is given by the relation NO2 is equal to Q into S naught minus SE divided by F into 10 power 3 gram per kg. We are converting it from kilogram to gram. Okay, minus 1.42 px. So here the px is the mass of the sludge wasted each day. This is the weight of the sludge. Okay, and this px is given by y absorbed into q into s naught minus se divided by 10 power 3 gram per kg. So this y absorbed is obtained from the equation y absorbed is equal to y divided by 1 plus theta c into k. So using all these formulas, we are going to find the mass of the oxygen required for the previous question. So here, first we need to find the y absorbed. So y absorbed is equal to y divided by 1 plus theta c into kd and the value of y is 0.4, kd is 0.07 and the theta c is obtained as 9.61 days, right? So substitute all the known values here. We will obtain the y absorbed as 0.239. So now you know the y absorbed value. Substitute it here to find the px, which is 0.239 into flow rate is 510 meter cube per hour. It is mentioned in this question itself. Okay. So converting the hours to days, so you are multiplying it with 24 again. Okay, and then S naught minus SC. Initial substrate concentration is given as 240, right? And the final is 11 mg. So S naught minus SE is 240 minus 11 gram per meter cube divided by 10 power 3. So now the px value is obtained. So the mass of the sludge is 669.91 kg per day. So now we can easily obtain the mass of the oxygen value. So mass of the oxygen is equal to Q into S naught minus SC. So again Q is 510 meter cube per hour. It is converted to days and 240 minus 11 divided by F. F is the food ratio, right? So it is obtained here. Uh, so it is obtained from the the F by M ratio is the food to microorganism ratio, and this F mentioned in the question is the fraction of BOD, fraction of BOD. Okay, so it is 67.5 percentage of the ultimate BOD. So it is 0.675. So the fraction of BOD converted is in this process is 67.5 percentage. So we have to multiply it with 0.675 into 10 power 3. And then minus 1.42 into px. Substitute the value of px obtained here. If you solve this, you will obtain the mass of the oxygen as 3201.26 kg per day. So this much kg of oxygen is required. It is mentioned in kg. The question asks us to find the volume of air supply. Okay, so to convert it to volume percentage, first we have to know how much is the mass fraction of oxygen in the air. In terms of volume percentage, it is 23%. So it is 0.232, and the density of the air is supplied at the temperature of 25 degrees Celsius as given in the question. So at the 25 degrees Celsius temperature, the density of the air is 1.185 kg per meter cube. Okay. So now we can easily calculate the volume of air. Also, one more thing given is only 10 percentage is the efficiency of this oxygen transfer. So whatever you are supplying in that one, only 10 percentage is utilized in this process they are telling. So you have to calculate the volume of air for this 10% efficiency. So just divide the mass of the oxygen by the density of the air and the fraction of O2 in the air and the efficiency of O2 transfer. So you will obtain 1,16,443.33 meter cube per day. So this is the answer given for the volume of air supplied to the plant. Okay. Any doubts so far in the activated sludge process based problem? Shall we move to the next one? Okay. We'll move on to the next problem. So this problem is based upon the trickling filter. Okay. The question is determine the depth of the low rate trickling filter that has the diameter of 3 meter. Hydraulic loading is 0.17 meter cube per second. The influent and effluent BOD is given as 260 and 50 mg per liter. The unit operates at 27 degrees Celsius. Empirical constant M and N are equal to 1, and K value is given as 0.1 meter per day for the 25 degrees Celsius. Okay. The packing media are the rocks which have the porosity of 0.4 and the sphericity of 0.6. The geometric mean size of the rocks are 70 mm. Okay. So these are the data given. So the question asked is to determine the depth of the low rate trickling filter. So to obtain the depth of the low rate trickling filter, we have to use this equation. Note it down, which is SA which is SE divided by SI. So please note down this equation. This is the general equation. SE divided by SI is equal to exponential of minus KL AS power M A by Q whole power N. So here the M and N are the empirical constant, and Fe is the concentration of settled effluent from the filter, and Si is the concentration of influent to the filter. Okay. And K is the empirical rate constant, and L is the filter depth here. This is what we are going to find. And AS is the specific surface area of the filter. So the specific surface area of the filter is equal to surface area of the filter divided by volume. So now this capital A is the cross-sectional area of the filter and Q is the wastewater flow rate. So now we know M and N are equal to 1. So this equation will become SE by SI is equal to exponential of minus KLA is A divided by Q. Okay. So we have to find all the unknown parameters to substitute here. So initially we know the K data for 25 degrees Celsius, but the unit is operating at 27 degrees Celsius. To find the K at any temperature T, we can use the given data K25 and you can derive the value of K at any temperature T by using this equation, where Kt is equal to K25 theta into 1 minus 25. Theta is always constant, which is 1.08. Okay, this is the value of theta. Just substitute the K25 here, which is 0.1 given in the question, and 1.08 power 27 is the temperature, unknown temperature K value, and 25 is a given temperature K value. So T minus 25 is 27 minus 25, which is 2. If you solve this, you will obtain the K value as 0.1166. Now the K is known, and we already know the SE value, which is 50 mg per liter, and SI value, which is 260 mg per liter. Now K is also obtained, L is to be found, AS is the surface area, specific surface area. To obtain this, we have to use this general equation. Okay. AS is equal to 6 into 1 minus epsilon divided by 3 D. This diameter is a geometric mean size of the packing material. And this one is the sphericity of the packing media, which is given as 0.6. And the porosity is given as 0.4. Just substitute the value. So 6 into 1 minus 0.4 divided by 0.6. And the geometric mean size is 70 mm. Convert it to meter, 10 power minus 3 or multiplying. So the value is 85.71. Okay. So now the specific surface area is also obtained. We have to find the area. Area, cross-sectional area is given by pi by 4. 35 is the size of that filter. Okay. So if you square this one, you obtain the value of 962.113 meter square. And given the flow rate is 0.17 meter cube per second, everything is in days, right? So we just convert this seconds to day by multiplying it with 3600. So in a day, 60 minutes are there, and for a minute, 60 seconds are there. So 60 into 60 is 3600. You will obtain the flow rate as 14,688 meter cube per day. Now the Q is also known. Only unknown parameter is the L, which is the depth of the filter. Substitute all the values. 50 divided by 260 is equal to exponential of minus 0.116 into L, and AS is 85.71. A is 962.113 and Q is 14,688. So the value of L is, if you solve this one, you'll obtain it as 2.52 meter. So this is the depth of the filter used in the trickling filter. Okay. So this is a similar problem. Determine the depth of a low rate trickling filter. Diameter is given as 45 meter. Okay. Here the diameter is given as 3 meter. Hydraulic loading is 0.13 meter cube per second. So the loading flow rate is given. Influent and effluent BOD are 255 and 20 mg per liter. Unit operates at 27 degrees Celsius and M and N are equal to 1. K25 is 0.1. Packing media or rocks. Porosity is 0.6. Sphericity is 0.9. Geometric mean size is 8 mm. Only the values are different. So we know the formula. SE by SI is equal to exponential of minus KLAS power m into A by Q whole power n. M and n are equal to 1 and the K value is to be found for 27 degrees Celsius. So we know the equation K27 is equal to K25 into theta, which is 1.08. So power 27 minus 25. Now by solving this, you will obtain the value of K27. Okay. And L is to be found. S is obtained by using the equation, this equation, where the porosity and the sphericity are given in the question itself, which is nothing but 0.6 and 0.9. So you have to find the AS value. Next is the geometric mean size is also given, which is 80 mm. You have to convert it to meter. Now this L can be obtained by minus ln of 20 divided by 255, which is nothing but the values of this SE and SI. 20 divided by 255 into 0.13 meter cube per second is the flow rate. Convert the second into hour, hour to day, divided by 0.1. Okay, 0.1 into 1.08 is the theta value. It is assumed here. So just this is the value to determine the K. Okay, 0.1 into 1.08 or 27 minus 25. This 0.1 is because K25 is 0.1. And here you are deriving the AS. 6 into, which is nothing but we are using this equation. 6 into 1 minus 0.6, which is the porosity, divided by 0.9, which is the sphericity, into geometric mean, which is 80 into 10 power minus 3. Okay, and now we are deriving the cross-sectional area. So the cross-sectional area is pi into 43 square divided by 4. So if you solve this one, you will obtain the L as 5.06 meter. Okay. So now the next question is for high rate trickling filter. The question is determine the size of the high rate trickling filter in the sewage flow, in which the sewage flow rate is 4 mld with the recirculation ratio is given here as R. R is given as 1.5 and the BOD of the raw sewage is 260 mg per liter, from which 30% BOD is removed in the primary settling tank and the desired BOD of the final effluent is 35 mg per liter. So we know that raw sewage water is having 260 mg. Okay. So in the primary settling tank, we are passing the sewage water. So this raw waste water is having the 260 mg per liter of BOD and 30% is reduced in this primary treatment. So 30% is reduced means in this 260 only 0.7. 70% is the incoming BOD of the trickling filter, which is nothing but 182 mg per liter. And the desired desired BOD of the final effluent is 35. So this is the effluent BOD from the trickling filter. So that is why naught is given as 35 mg per liter. So this much BOD, 35 is the outgoing BOD from the trickling filter and 182 is the incoming BOD to the trickling filter, because 30% is already removed in the primary settling. Now we know the Yi and Y naught. Okay. To know the efficiency, we already know, right? Efficiency is determined by Yi incoming value, outgoing value divided by the incoming value. This is how the efficiency is calculated. The question here is to determine the size of the trickling filter. To determine the size, the formula is, so here the size means we are going to find the diameter. To find the diameter, you should know the area of the trickling filter. To know the area of the trickling filter, you should know the volume divided by depth. Okay, so this is obtained by this equation. Indirectly, we are calculating the dimension of this trickling filter. Okay, so now with this, the efficiency is first calculated, and then the BOD load on the filter is. So the BOD load is 182 mg is incoming, but the total volume is 4 mld, right? So we have to multiply it with 4 mld. So now you know the incoming load as 728 kg per day. So this is the W, organic load per BOD load in the kg per day. So now we obtain the W value. Next is the recirculation factor. This recirculation factor F is obtained by 1 plus R divided by 1 plus 0.1 R the whole square. This is the general form. So now substitute the recirculation ratio R value to 1.5 and obtain the F value. So now you have obtained the F value, W value, E value. Only unknown value is the volume, right? So with this you will obtain the volume of the uh, since you know the efficiency as 80.76, you will derive the volume of the tank as 1314.06 meter cube. Now we know the depth of the tank as 1.2 meter. Just divide the volume by depth to obtain the area, and the area formula is pi by 4 d square. In this one, you will obtain the d value as 37.349 meter. Okay. This is how we will solve this problem. Only one question is remaining. The time is up. I will solve that question also. Okay. So now coming to the last question, the wastewater flow from the small community. This is very simple question. Okay, the wastewater flow from a small community averages 3,400 meter cube per day during the winter and 6,600 meter cube per day. The flow rate are different in winter and summer. Okay, the average temperature of the coldest month is, so for the winter the temperature is 10 degrees Celsius and the average temperature for the warmest month. So for summer it is considered as 30 degrees Celsius. The average BOD5 is 200 mg per liter with 70% being soluble. So the incoming BOD is 200 and only 70% is soluble. The reaction coefficient K is 0.25 per day at 20 degrees Celsius and the value of temperature coefficient is 1.09. Prepare a preliminary design for a facultative pond treatment system for the community to remove 90% of the soluble BOD. So we are going to design a facultative pond treatment. Okay, so this is a kind of lagoon system. So that pond treatment system should have the efficiency of 90%. In that way, you have to design the system. So they are asking you to find the volume of the facultative lagoon, which has the capacity to remove 90% BOD. So the incoming BOD is 200 mg per liter, right? So in this one, 90% you are going to remove. This is the removal rate, and only 10% should be there in the effluent they are telling. That means only 20 mg should be left out in the effluent stream they are telling. 20 mg per liter. In such way, you have to design the volume and then you have to find the dimension of the three square lagoon in series. If we are using three square lagoons in series with a depth of 1.5 meter, they are asking you the dimension again. Okay, it is very simple. First, there are two different seasons. We have to consider this. In the winter, the temperature is 10 degree. In the summer, the temperature is 30 degree. And the K value given you is for 20 degrees Celsius. Now we know the general formula, right? So, K at any temperature T is equal to K at the given temperature. Here the given temperature is 20 into 1.08 or 0.9. So this is a constant value in use. So the given temperature is 20. So T minus 20. This is the general formula you are going to use. So it is 0.25 given in the question. For 20 degrees Celsius and for 30 degrees Celsius, we are calculating the K30 and K10, which is 0.592 and 0.106. Now we have to estimate the volume of the lagoon by using this equation. Okay, this is your general equation. which is S by S naught is equal to 1 by 1 plus K into V by Q, where K is the reaction rate, V is the volume, and Q is the flow rate. This V by Q can be written as theta. Okay, so S value is which is the outgoing BOD. Outgoing BOD should be for 90%, outgoing BOD should be 20 ng. So 20 divided by incoming BOD is mentioned as 200 mg. So 20 divided by 200 is equal to 1 divided by 1 plus the K obtained for summer is 0.592. Okay, and V divided by Q is flow rate is 6,600 meter cube per day. If you solve this, the volume of lagoon is V is equal to 1,337.84 meter cube for summer. Then substitute the K value. K is nothing but the reaction rate. Okay, reaction rate for winter at 10 degrees Celsius 0.106. Substitute it here and you will obtain the volume as 2,88,679.24. Okay, so this is the flow rate for winter, this is the flow rate for summer. Substitute the respective reaction rate in the equation. You will obtain the volume of the facultative lagoon to remove 90% soluble fluid. And the second part is to find the dimension for the three square lagoons in series. The depth is given as 1.5 meter. The same formula but in different way because it is a series of three square lagoons. So the formula is Sn divided by S naught is equal to 1 divided by 1 plus k theta by n whole power n. Okay, this is the formula we are going to use. See the schematic diagram. This is the lagoon 1, 2, 3. Each of depth 1.5 meter. Initially, the flow rate is mentioned as Q. S naught is the amount of BOD going into the lagoon 1. And the BOD coming out of lagoon 1 is S1. The BOD coming out of lagoon 2 is S2. And the BOD coming out of lagoon 3 is S3. The flow rate is same. Okay, depth is also same. Use this formula and you know the K value for the summer as well as winter. This is just the reciprocal of this equation to avoid these things. So S naught by S is equal to 1 plus K into Pi by N into Q whole power n. Okay, that is how this is written. So 200 by 20 is equal to 1 plus K value for summer is 0.592 into Vi is going to be formed divided by 3. So there are 3 lagoons. So N is 3, flow rate is 6,600 whole power 3. So now the volume is 38,611.16 meter cube. And for the winter, 200 divided by 20, just the reciprocal of this one is written here. Okay, 200 divided by 20 is equal to 1 plus. Again, the K value for winter is 0.106. Substitute Vi divided by 3 tanks are used. 3,400 is the flow rate in the winter. Whole power 3. Okay, N is equal to 3 here. So now the volume of the tank in the winter is 1,11,087.11 meter. Okay. Now we have solved the problems for activated sludge process, trickling filter, as well as the facultative pond system. Thank you. Do you have any doubts? Do you have any doubt in today's session? Okay. Thank you for joining the today's session. So every week, Saturday 3 to 5 p.m., I will be handling the live session for this coursework. See you all in the next class. Thank you.